Okay, we can get started.
Okay, sounds good. Okay, so intro to kernel exploitation. Um, I thought that I would first give a general kernel overview. Please just ask any questions that you want at any point during the presentation. If I end up assuming some previous knowledge, just any questions are good questions. But I decided to do like a general overview of kernel in general. So a little bit of the kernel user space separation and also a little bit of the memory corruption concepts that will help us here, like what is ROP, how it works, etc. So starting from the kernel overview, the kernel can do all sorts of things directly, like reading. Sorry, I should probably introduce myself first. Okay, so I'm Pedro. I'm a friend of Phineas. Uh, I do blockchain security for RSec. I do a little bit of kernel research on the side sometimes. Uh, Hunting for 0 days, exploiting 1 days, that sort of stuff. And yeah, so that's what I'm presenting about today about kernel. And okay, so the kernel can do all sorts of things directly, like reading and writing from anywhere in disk. And the user, on the other hand, has to ask the kernel to do that kind of stuff on their behalf. So the user can ask the kernel to fetch some file from disk and make that file accessible for the user process. And that asking is done through the syscall API. So you have a bunch of syscalls, which are basically entry points that can be called from user space to do specific stuff that only the kernel can do. So a lot of permission and privilege checks, they are done in the kernel. And for that reason, the kernel is a very interesting target to compromise because we can break those security boundaries. And that's more or less how the syscall stack looks like. So imagine you want to open some file as readable and writable for your process. So the user will invoke the syscall by executing the syscall instruction and passing a syscall number, which in the kernel side of things will be used to select which syscall we want to call. So routing your request to the specific syscall you want to invoke. So let's say you call in the open syscall, it will open a file in the disk, it will create a file structure on the kernel side, and we'll associate this with a file descriptor, which is basically a session ID for the user process to interact with the file. And then you can read and write the file as long as you have permissions. So that's pretty much how it works. Another interesting concept is device drivers, which basically sometimes you have vendor-specific hardware that isn't managed by the core kernel. For example, let's say you have a cell phone like a Google Pixel or some other model. It has its own system on chip with its own peripherals, and that's all unmanaged by the kernel. But the kernel, the code that will manage the hardware has to run in the same context as the kernel. So the Linux kernel, it allows you to load what is called Linux kernel modules in runtime, which are basically extensions to the kernel code that you load in runtime and you can interact with it. Most device drivers, the way they expose their API to user processes is by creating a pseudo file in the /dev file system, uh, which is basically where you store you have file system entries, which are inodes registered by the kernel module. And once you want to interact with the kernel driver, what you would usually do is that you would open this /dev entry of the device driver. So you're gonna do the normal context switch to reach the syscall handler. The syscall handler will reach the open syscall, which usually the open syscall, it will go through the file struct and look for the file operation that it wants to execute, because that's usually file system dependent. So if it's a file on ext4 file system, it will call the ext4 open file operation and so on. But if the inode of the file was registered by a device driver, instead of the file operations being backed by file system implementation, they will be backed by the device driver. So this will then be routed to the device driver. So all of this, we can call this just routing. This is routing your request to the device driver API, which is back here. And then you can open the device driver, which will return a file descriptor associated with a file struct that is backed by this driver. And then you can, let's say, if you call read on that device driver file descriptor, you'll be calling read from the file operations defined by the driver developer. And then there's IOCTLs. When you're interacting with a device driver, it's usually inconvenient to have to implement a syscall handler, a file operation handler, for each different function that you want to expose to the user, especially because the arguments for each of those file operations are different, and some of them have additional side effects. For example, if you call mmap with the file descriptor of your device driver, it will actually map memory to your process. So you will execute the handler, but you also have other side effects that you might not want. So there's the IOCTL syscall, which is essentially a file operation. Now, let me check questions real quick. No questions so far. Okay. So it's essentially a file operation that all it does is execute the IOCTL handler of the driver. And the way it works is that you pass in the file descriptor to route it to your driver, and you pass in a request parameter, which the file descriptor, we can call like all of the routing a transport layer, but the request is where the application layer starts. So basically, it will reach the driver IOCTL with this request parameter, and it will usually be used in the IOCTL handler coded by the driver developer to select which routine to call. So through that mechanism, using an IOCTL, you can expose multiple commands to your user application. So, and then there's a third argument, which is a user-provided 64-bit value, which is usually a pointer into userland to pass in structured data in your request. So the stack usually looks more or less like this. So you have your user process, which will open the device driver on /dev, and then there's all the routing. You reach the open handler in the device file operations, which will return your file descriptor, and then you can call IOCTL on the file descriptor. So let's say you have some hardware, some LED light, and you can make the light red. You would call an IOCTL and passing the command that you want, and that command is specific to the driver code, to the API that is exposed to the user, and then you will send a request to the device IOCTL, and there's usually going to be like a switch statement, and in case the command matches this, it will go down the routine that makes the LED red, let's say through calling, through sending information through GPIO to the actual hardware, which is something, let's say, the kernel was able to do but not the user. So that's why you would need to go through the driver. So in red is the code that we're interested in understanding and compromising, because it's where most of the entry points to the driver logic uh, starts. So the data flow from the user input to any syncs, so anything that actually processes the user data, the entry points will usually start here. So we're moving on from this basic kernel overview and device driver overview to an exploitation overview before we can move into actually exploiting a driver. So before we move on, I would maybe want to ask if anyone has questions about the stack that I presented before.
We good. We're gonna put some questions at the end.
Okay, so we're doing questions in the end. Okay. Um, so as far as I know, you guys already had another presentation that talked a bit about exploitation. So maybe buffer overflows were already introduced. But as far as I know, they didn't introduce ROP. So basically, in modern systems, you have a protection called NX, which makes it so the stack memory is readable and writable, but it's not executable. Which means you can simply add some shellcode to your stack and execute that. And the most common workaround for those for that protection is usually code reuse attacks, and the most common one is called ROP, which basically you want to find pieces of interesting code in the already existing code memory, which is executable, and if those code pieces they end in a ret instruction, you can chain them together, and I'll explain how. So that's probably the most confusing slide of the presentation. It doesn't get any worse than this, but this is not important for you to know how to write a ROP chain, but important for you to know how it works and why it works, which I believe is important to know. So first, we should understand how it works in the assembly level, in the machine code level, when you want to call a function in x86. Usually, your function will execute the call instruction. And the call instruction, it does two things mainly. It will first store its own instruction pointer in the stack. So the instruction point here would usually point to the next instruction, but we are redirecting the control flow to another function that we're calling, and when this function ends, we need to be able to restore the control flow in the caller function. So the way this is done is by storing it on the stack. So imagine the stack pointer is pointing here. We're going to store the IP register and increment the stack pointer here, and then redirect the control flow to the callee function. And then the callee function is also responsible for respecting the calling conventions, which the next thing it's going to do is storing the base pointer, which is a register that is supposed to always point to the start of the current stack frame, so the point to the start of the stack frame of the current function. We need to store that because we're going to need that back when we're redirecting control flow back to the previous function. So we'll store the base pointer, and the stack pointer is incremented again by pushing. Sorry, that's actually decrementing because the stack grows from the high addresses to the low addresses, but I think you get the point. So you're gonna decrement the stack pointer by pushing this onto the stack, and then it will save its the current stack pointer to BP, because that's the BP that we're going to use while executing our function. And then we allocate space for our local variables by subtracting the size of the total of the entire local variables from the stack, and this is how the stack frame looks at the start of the execution of the call leaf function. Okay, so then you execute your code. You're gonna have a bunch of pops in your assembly. They're gonna little by little increment the stack pointer back to somewhere here, which is where it should always point at the end of the execution of your function. Okay, so when it reaches that point, we should now execute the returning routines, which essentially means that we'll have to restore our base pointer back to what it was previously, and execute a ret. The ret instruction, it is functionally equivalent to a pop IP instruction. So basically, you just consume whatever is at the top of the stack and put that in the instruction pointer, which will then redirect the control flow to whatever is on the top of the stack. And that's the interesting mechanism that we're gonna abuse for ROP. So control flow is redirected back to where we're executing previously, and everything works just fine. Okay, so assuming you have for example, a buffer overflow in your local variables, so that's why buffer overflows are exploitable in the first place. You're gonna overrun the stack until you reach this saved value, and when you reach the return, a corrupted value will be popped, and instead of the control flow being redirected back to where it should be, it will be redirected to a arbitrary position in the code. And the way we abuse the mechanism to kind of glue different code pieces together to do a ROP chain is, let's say you put a pointer on top of your corrupted IP to point to your first gadget, and your first gadget is some instruction you want to execute, followed by a ret instruction. So your instruction will be executed, and then a ret will be executed. And as we already know, a ret instruction basically just gets whatever is on the top of the stack and runs that. So if we can overrun the stack all over, we can just add a bunch of gadgets that end in a ret, and whenever the ret is executed, it will consume the next value on your ROP chain, and then the next and the next. So it looks more or less like this. So you have your buffer overflow, you overrun the BP, you overrun IP, and when your function returns, it will execute the instruction pointed by your corrupted IP, and it points to instruction A, but instruction A is followed by a ret. So then we have to see whatever is next on the stack. We pop that onto the IP, which will cause it to be executed. And then we go back to instruction B, which is followed by a ret, and this process goes on, and you can execute any instructions that you want as long as they are already in the code and that they are followed by a ret, because you can connect them together. You can so that's return oriented programming. Okay, so additionally to ROP, there's one concept that we have to know to move on, which is another protection. We already mentioned NX, which is why we have to use ROP in the first place, but there's another protection that we'll have to bypass, which is the stack canary. So as you can see here, all of this only works because you're overflowing linearly, and then you can corrupt whatever is following your local variables. But the way the stack canary works is that they add a guard value between the local variables and the saved registers on the stack, and this guard value, before returning, it is verified to have remained the same. So if the guard value changes for some reason, it means that the stack was corrupted, and this is detected, and the kernel will crash. So the way you usually bypass this is either through the same vulnerability or through a different one. You want to leak that value from the stack somehow and use it in your payload, because when you're overflowing, you're gonna fake values on those pointers, but the canary is on the way. But if you fake the canary to be the same as it was before corruption, it won't be detected, and you can continue with your exploitation. So the common workaround is to leak this somehow. Okay, and I guess now we have essentially all we need to start actually exploiting a vulnerable driver. So I wrote a very simple one. I'll show you the code briefly. But basically, this is the work environment that we're all working on. It's quite annoying to test that kind of stuff directly on your machine, because whenever you do something that causes the kernel to crash, it's your machine that's crashing, and you have to reboot, and that's just a pain. So usually we use QEMU to run the kernel that we're testing with and the drivers that we're testing with inside a VM. And it's also very convenient that QEMU has a flag that allows you to expose a GDB stub, so you can connect GDB remotely and debug the kernel. And whenever we're doing ROP, it would be inconvenient to manually search for the bytes that translate your instruction in the executable memory. So you can just get the binary and use a tool called Ropper to output all of the possible interesting gadgets. Okay, so I'm running with QEMU, and I can boot my VM into the kernel that I want to work with. And the module is it's already loaded, and we have the /dev entry over here, and you can already interact with the module. If we want to use GDB, we can do target remote. The default port that QEMU uses is usually 1234, and then we're debugging the kernel. So that's relatively easy to set up. And now I think we should probably move on to the code of the driver. So as I mentioned previously, the API that will be exposed to the user processes is the file operations associated with the device driver file. So that's what we should probably look first. And we can see that we have the release file operation, which is just some cleanup routine that I execute when closing the file descriptor, just freeing some heap objects, not too relevant. And this is the routine where most of the code logic lives. So we have the kernel side file structure associated with the file descriptor that we use to interact, which is what is used to route a request here, and also interesting to save some kind of session specific information. I'll go more into it later. And CMD here is the request parameter that is used to select the routine. So I just do a switch statement and select which function I want to interact with. So this is user controlled, and arg here is the third argument of the IOCTL syscall passed by the user, which I use as a pointer into userland to copy a structured request. So there's the UXS API, which is a way for the kernel to copy data to and from user memory. So then I use copy from user to dereference this user pointer and copy that data into this buffer, which is basically a simple structure with a length and the pointer to the user data that we want to copy. And then let's say I want to go to the write buff routine. The write buff routine will allocate a kernel buffer in the heap and copy the data pointed by the request I showed previously to that buffer and store it in the private data of the file. That's why I said that the file is interesting for saving session-specific data, because this file structure is associated exclusively with the file descriptor exposed to your process. So I want to save this globally. I don't want this reference to be lost when the function returns, but I don't want to just add the pointer to some global memory, because that's accessible globally. I want this to be accessible only by the process that has my file descriptor opened. So I add it to the private data. I set the private data to be a pointer to this buffer that we allocated, and that's all of the write buff routine. You have the rebuff function, which will get this buffer back from the private data, and it will copy those bytes. We want to get them back in userland. So the functionality is pretty simple for this driver. We just create some buffer in the kernel. Oh, zoom in. Okay. On terminal. Okay. Sure. Is that good? Okay. Okay, so we can write to a buffer in the kernel and then read that buffer back to userland. And the way this driver decides to do it is, first, it has this temporary local variable buffer, which has the fixed size of 64. But if we look at the IOCTL, when we copy the request to allocate, we see that the size is limited to max length, which is 512, which is bigger than 64. And if we follow down the call chain to write buff, the size that we pass in the write buff request is used to allocate the buffer and set the size that will be stored in private data. So later on in the rebuff, when we get the lane back from the private data, it can be anything from 1 to 512. So this would cause this variable to overflow. So that's the first thing. The second thing is when we're reading back those values, it will allocate a heap object called output, and it will copy the temp variable to output, but it will use the new request length, which is not to be confused with this length. They're both controllable by the user, but this one was set on our first request when we wrote to the buffer. This one is the new one that we're using to read the buffer. So imagine, for example, that we decided to play nice and made this length smaller or equal to 64, which will not overflow this buffer. But then, when reading the buffer back from temp, we decided to do a bigger length, so bigger than 64. Then the overflow will not happen, because we decided to do this to make this small and this big. It won't overflow, but it will overread. So in this function, we have two different bugs. We can overread here, and we can overflow here. Okay. And then the output object is copy to userland. So since when we read temp into output, we can overread, we can leak special values from the stack, including the stack canary, and then the output buffer will be copied to userland, which means userland can see the stack canary and bypass the protection. Okay, so moving on. So just a quick overview. So we know that the vulnerable driver implements two commands, the write-buff command and the rebuff command. And the write-buff command will allocate an object in the heap with user-controlled size and content, and then rebuff will copy that buffer into a stack variable, which is fixed to 64 bytes. So that's where the overflow happens. Okay, I should probably have to show this first. So, but what's the vuln here? It's a buffer overflow. So, moving on. Just a quick overview of what the goal is here. First, we want to trigger the bug such that we can read the stack canary, and then we want to trigger the bug such that we can override the saved IP to hijack control flow and kick off the rob chain, so we can execute arbitrary code and become root. And then now we can go into the nuances of this. So okay, we're doing rob, but how should a rob chain look like? Because when you're exploiting a userland program and you have arbitrary code execution, it might be intuitive to some people that you want to maybe call the system function with bin and sage to get a shell. But if you think about it, that doesn't really make sense if we're exploiting the kernel, because we're not in the context of a remote attacker trying to get a initial foothold. We're in the context of an attacker with an initial foothold that wants to escalate the privileges. So what we want to do here is become root somehow. So the rob chain will be fairly different. We want to know a few things first. First is that there's a symbol in the Linux kernel called initcred, which is a symbol that points to the cred structure of the init task, which is the first task created when you boot your kernel, and it's a task created by root. So the cred structure here should be a root cred structure. So whatever process holds those credentials should be a root process and be able to do whatever root can do. And then we have to know about the commitcreds function, which is a function that takes one argument, and that argument is supposed to be a pointer to a cred structure. It takes the cred structure past this argument and commits it to the current running process. So it makes it replaces the cred structure of your process with whatever cred structure you pass in as argument. So we can say that the goal of any shellcode or rob chain in this environment would be to maybe call commit creds with initcred as argument, because this will make us become root, right? And so only 3 gadgets, and only one of them is an actual rob gadget, which is pop RDI red. This seems too good to be true, right? It's too easy. And it is, because at this point of the exploit, we have become root. So we replace our creds. It's almost a win. But we corrupted the stack and the control flow. So if we just let it continue execution and return now, the kernel will just crash with a corrupted stack. What we want to actually do instead is switch context back to userland. So one thing that we should understand here is that it might be counterintuitive to some, but the userland and kernel, they're not different tasks that run separately, and you just request something from the kernel and the kernel responds like a web API. That are just two remote things. Uh, because that wouldn't work if you only had one CPU, right? What you actually have here is different contexts. So when you do a syscall from the kernel, you're not like it's not an RPC. You're not calling something remotely. You're changing context, and that's done by saving your userland registers, entering kernel mode, executing whatever you want in kernel mode, and then going back to user mode in the same CPU. So there's this function called swap.js, restore regs, and return to user mode that does exactly what the name says. It's executed when you finish doing whatever kernel tasks that you wanted to execute, and now you're returning to user mode. So you called into syscall, the syscall was executed, and now you're returning to user mode. We want to use that to, after we changed our privileges, we want to go back to userland safely. We want to land on our user process so we can continue to execute code in userland as root. Something that I would like to add is that this function, it pops, like in the very start of the function, it pops a bunch of registers that we're not interested in, and since we would need to take account of those and add some dummy registers to a RUP chain. Instead, I decide to just jump directly to the interesting part of the function that only does the context switching. And we can call the code that we jump to, which lives inside this function, the user mode trampoline, which is the function that will switch us back to userland. And this trampoline, what it does is it will pop some more values and use those values as the userland registers when you return. So a RUP chain finally would look something like this. You have your padding, which is so that you can reach the end of the stack. You have your canary that you leaked from the kernel with the overread vulnerability, and then you have the saved BP value, which doesn't matter for us right now, and then you have your first gadget, which is pop RDI red, and you have the init cred. So when the function returns, pop RDI will be executed, and it will consume whatever is next on the stack, which is init cred. So this is consumed by pop RDI. The stack pointer is moved down, and RDI becomes a pointer to the init task credential. And then return is executed, which will consume the next value on the stack and put it on the instruction pointer and execute. So commit creds is executed with init cred in the RDI register, which is functionally equivalent to calling commit creds with init cred as argument. And then we finally want to return to user mode safely. So we execute the user mode trampoline, and we put on the stack the registers that will be consumed by the trampoline. So some values that will be popped and used as the registers when switching to user mode. So your user mode stack pointer, your user mode CS flags, your user mode instruction pointer, we're gonna save all of that here at the end of our ROP, because that's what will be the state of the registers when we get to userland. I wrote an exploit for the purpose of the lecture. So as I was discussing about the so someone okay, I'll comment on the KSR leak at the end of the talk. It's a very interesting topic. But yeah, um, we have the save state function here, which is basically just storing the registers that will be needed to restore the userland context when switching back. So we just save those registers at the start of the execution. We open the module that we want to interact with. We get the file descriptor, and we call write buff with a normal size that will not overflow. We don't want to overflow, because if we did overflow now, we would be overriding the values that we want to leak. So now we just leak the stack canary into buff. So now we know that buff will contain like a bunch of A's followed by the stack canary followed by whatever values were on the stack. And then we don't even need that anymore because it's already in buff. And then in the offset in which the IP, the stored IP value was, we put our first gadget, which is pop RDI. And on the next offset, we add the rest of our gadgets and so on. So this is the same as we saw on the slide. And now we have crafted our payload, and we just want to write that to the kernel buffer, and then trigger read, because this is what will trigger that to be copied onto the stack and corrupt the control flow. So after this exploit was ready, I was stupid enough to recompile my kernel, so the offsets might have changed. I'm not really sure. We're gonna find out now. If they have changed, I'll just have to update my gadgets. But if they haven't, yeah, it works. Okay, so we have a regular user that cannot read, let's see, shadow. And then we execute the exploit, and we have become root, and now we can read, let's see, shadow. Nice. Okay, so that's, I guess, the minimal introduction to kernel exploitation. It won't get any simpler than that. But moving on, you can have like there's a bunch of beginner resources that I decided to add because even if that's the basic of kernel exploitation, it would be a lie to say that kernel exploitation is not a advanced topic in the first place, right? So for some people, this might already be a difficult talk to swallow, but there's a bunch of resources that you can refer to first, and then if you already have all of the background, if you want to move on and actually learn a lot more about kernel and be able to write real life exploits, I also put in some more advanced resources. And someone asked about the KSLR leak. I saw that. That was hilarious. So for those who are unaware, KSLR is the equivalent in the kernel to ASLR, which is another exploit mitigation, which works by randomizing the base address where you load some memory section. So you can randomize where you're gonna load the kernel code, and then when you want to do ROP, which is what we just did, you would have to account for KSLR. So you would have to get a KSLR leak, add that to your gadgets, and then it would work. And the reason why it would work is because even though you randomize the base where you load the kernel code, the offsets between the different parts of the code have to be deterministic, right? Because if you have some instruction which is at the start of the code plus 0, let's say it's the first instruction, and you have some other instruction which is at the start of the code plus 35, this 35 should remain. Otherwise, it would be changing the code, obviously, right? So um, once you get a leak of any pointer that points to your memory that was randomized by KSLR, you can calculate any other address, and that's how ASLR works and how it's bypassed. And for years and years of kernel exploitation, we always had to somehow get a leak, sometimes requiring a separate vulnerability just to get a leak. And all of that time, there was a pseudo file in the slash sys file system that that had a KSLR leak. I think I might have, because I was playing with it earlier. No, I don't have it anymore. I was playing with that earlier, but basically, it was recently discovered that we were leaking KSLR for no reason because there was a free leak that we could just read, and this was live for like 17 years. So like 17 years of kernel exploitation, we're doing extra effort for nothing, because so one of the memory sections of the Linux kernel ELF binary is the notes section, that is supposed to be public, and any user can read it by checking the sys kernel notes file. And it has some stuff like the kernel ELF headers, some metadata. And when you compare your kernel with Zen virtualization, it was adding some data that contained a kernel pointer that was randomized by KSLR. So by reading this file, you were able to easily leak KSLR, and that was there for years, and no one knew about it. um, but yeah, that was pretty funny. Do we have more questions? Oh, we do. Okay. How does a remote kernel exploit work? That's usually a lot more complicated, because so most real life kernel exploits, they don't exploit like stack bugs like we saw here. These bugs, they're almost extinct, and they're much harder to exploit nowadays. We usually exploit heap bugs like heap overflows, use after freeze, and these bugs, they usually don't consist of exploiting data that is already uh, in memory, like the stack registers that we just saw. It usually consists on um, doing what some people called heap feng shui, or heap spraying, which is uh, which is uh, triggering the allocation of objects that may contain interesting data. For example, you have a use after free bug, which is you can free a heap object and still use it later. You could, for example, let's say it's a heap object that you have a write primitive to. You could free it, and then you reallocate it with some other structure by calling some syscall that will force it to be allocated and override that. So you usually need to have some control of the memory layout, and to be able to allocate some interesting objects that you might want to corrupt. And that's much harder remotely, because there's not much that you can force to happen remotely. um but yeah, there has been some remote kernel exploits recently, specifically in subsystems that have a lot. I'll fetch one real quick, but specifically in subsystems that there's a lot of stuff that you can do remotely. um, Relatively recently, the Linux kernel added a Samba protocol implementation in the kernel, and there's a lot of different interactions that happen through the protocol. So someone was actually able to write a remote exploit. Uh, mm, oh, here it is. Okay. Um, and they actually wrote a RC exploit, but um, exploiting the kernel remotely is very limiting. Um, oh, sorry. Um, and I saw property I read gadget. Isn't RDI x86 specific? Yeah, it's x86 64 specific, which is the architecture that we're assuming here. If you want to do ROP, you need to do it for your specific architecture. If you want to do a multi-arc exploit, it wouldn't work in the first place because the exploit code was compiled to x86 64. But you would have to have multiple exploits. You would have to have one for x86, one for ARM, one for ARM 64, and once you land on your target, you can select which exploit you're gonna use. But yeah, RDI is x86 64 specific. Um, are the commit creds, incred, and swapshes functions available as gadgets in all exploits? Yeah, they are part of the kernel elf binary. So let me show you this. Let's run the exploit first, just to we can root. So you have this file. Great commit creds proc. So this can only be read as root usually. You can change that if you want, but by default it's only readable as root. And you have like the I disabled KSLR for the purpose of the lecture to make it simpler. So these pointers, they're not randomized, and they are the pointer to wherever in memory those symbols live. Commit creds is always there. The kernel needs that to work. Init cred is always that, and swap.js restore regs and return to user mode is also always there. So you can just find those here and use them in your rough chain, similarly to what you would do in a ret to libc attack. Oh, by the way, I sent Thinias a um, archive with the exploit that I wrote, the vulnerable driver, and all of that, so you can play with it. But I'm working from a ARM 64 laptop, and I'm working on x86. This works due to QEMU, but when compiling, um, when compiling, um, I'm using a cross-architecture toolchain. So if you're working from a x86-64 laptop, like most people, you can just remove that and also remove this when compiling the module. Um, oh, it's not here. Sorry. You can remove this. This is not necessary for you. It is for me because I'm working from ARM. But if you're working from x86-64, you can just remove that. And maybe remove that because it will fetch the host architecture. Let me see if we have more questions. Let me actually click the link to make sure that the KSLR link that they were talking about is the same. Yeah, it's the notes one. Okay. Do we have more questions?
All right. Hey, Pedro. I'm Chris. I guess I'm the coordinator of these beautiful students. So it looks like we don't have any more questions, but I wanted to thank you personally for spending time with us. And your talk was very much interesting. It's high level, but luckily we have a group of people who all know some stuff,
Nice.
right? And we will review your examples that you handed us to us, and yeah, review all these resources that you also presented. And um, I'm very much looking forward to seeing you again. And I guess
Yeah, me
Phineas is
too.
the one who's going to keep in contact. And yeah, wish you all the best. And yeah, thank you.
All right.
Come see us. Come visit us in Romania at one point.
Yeah, sure.
Yeah.
Thank you so much. Thank you so much for
Okay.
having me. Wish you very good luck, and hope you guys actually develop some interesting in looking deeper into kernel exploitation. It's a very interesting topic.
Yeah,
Uh,
it sure is.
all right. Thank you so much.
Thank you. Thank you again. Bye bye.
Bye bye.